First off, I'd like to thank the conference organizers for having me. Shout out to Hector Garcia for giving me the opportunity to talk here. But also thanks to my employer, TD Ameritrade, for letting me come out into the wild and have a chat with all of you. For those of you who don't know, so TD Ameritrade is a financial investment firm, online mobile brokerage. We manage about just over $1 trillion in client assets. So we're across the United States. We were voted last year or selected as the #1 overall broker by Kiplinger. We have, if you're a long-term investor, if you're thinking about retirement, goal planning, whether you want to trade online, mobile, we have all of these different products. We'd love for you to use them. Also, if you're an options trader, Forex, foreign exchanges, futures, we also have a wonderful platform called Thinkorswim. You should go check that out too. Additionally, we were also recently chosen onto the Forbes 2019 list of America's best large employers. We have an office, which is where I work in downtown Ann Arbor, right above Bar Louie. So come check us out. You can find jobs at jobs.tdameritrade.com. In addition to that, maybe just a little bit of culture, right, of what you see. This was just a couple of weeks ago. So this was right behind where our building is, and we have some special guests serving as baristas downstairs. And that is our CIO, Vijay Sankaran, as well as our CEO, Tim Hockey, serving, you'll see me down at the bottom here, right, getting a picture. So it gives you an idea, but more importantly, these cups have a very special message related to our company purpose, which is transforming lives and investing for the better. The key thing here is transforming lives first, right? And to a large extent, I do some of this in collaboration with some of my Pi Data co-organizers. So Dr. Patricia Schuster, as well as Ben Zeitlin, we co-organize the Pi Data Ann Arbor Data Science meetup. It happens monthly. All of our talks are recorded and posted on YouTube. So if you go check out Pi Data Ann Arbor, you'll find all of our past talks. We have one coming up on Monday. So go and check it out. It's at 6 p.m. Also, shout out to NumFocus and Midas, as well as TD Ameritrade for sponsoring our events. So with that, let's get started. So who am I? Why am I standing here? So I'm Sean. I like to say I'm a reformed scientist turned researcher, applied researcher. So I work at TD Ameritrade on something called the Exploration Lab team. So this is the technology, research, and development arm of the company. So I serve as a senior applied researcher as well as data science. And really what we're doing is that we're exploring new and emerging technologies, or in my case, oftentimes, new methodologies that might help us differentiate ourselves from our competitors. Now, who is this talk for? You might fit into one of these categories, right? Whether you're a data scientist, an engineer, maybe you're a people manager. Hopefully what you'll take away from this is maybe one of three things, right? First thing is that I guarantee you that you'll likely learn something new, a new technique for exploring time series data. Or number two, you'll be highly entertained. Or number three, you'll watch an individual rip through just over 100 slides in less than 25 minutes, okay? So what's the problem? What's the problem? We've all been through this, if we've ever stared at this, right? We get some manager or some business person telling us, hey, I've got some time series data. Now perform some magic, Dr. McFancy Pants, right? And your data might look like this. If you got 10 data points, small data, right? That's great. You can visualize it. You can look at it. What if we had 100 data points? It gets a little bit, it's still manageable, but still a bit nasty. 1,000 data points, forget about visualizing it, right? And then this, forget about it. And this is only 10,000 data points, right? And we've all felt this dread. And this is what I tend to look like, right? Just overwhelming dread. And oftentimes we wish that there was some special way, like a magic wand that I can wave to say, ridiculous, right? And take this scary thing and make it not so scary. Now, there are some typical ways to analyze time series data. Obviously, time series, that domain tends to be a very visual thing, so you can visualize the data. That's what you want to do. Another very nice thing that we can do is statistics. Take maybe mean, median, mode, maxes and mins. But typically, with time series data, we're not really interested in that global metrics, right? Or you can approach it using some Bayesian methods as well. Everybody's favorite, ARIMA models, right? So you start building autoregressive models. Then the next thing you might want to do is look at anomaly detection or outlier detection. But again, not perfect, right? Because in order to know what is an outlier or an anomaly, you have to figure out what is normal first before you can say what is abnormal. And also, when you see an anomaly, again, is it normal or abnormal now, right? Because it's a repeat. Now, if you really trust your data, we can get into forecasting, right? That you believe that your data is good enough to help you predict the future or guess at that future. And of course, everybody's favorite, when all else fails, more data, right? And I don't really recommend this, but you pick your poison. Now, when I say more data for time series, right, it can mean longer time series, so add more data at the end of it, or also reasonable amount of data, but more dimensions, so add additional different time series, right? And look at the relationships through the form of clustering, or sometimes you might even sort of stretch and compress your data using dynamic time warping. These are very classical methods. And then obviously it's hammer time, right? We're looking for a nail to hammer. So let's choose deep learning. That's another very common method these days, right? And I took this quote directly from the conference website. And it says that there are lots of conferences these days, and almost all of them promise new and magical insights that will surely revolutionize the way that you work. And at the bottom, right after this, it says, this is not one of those conferences, right? And I tend to agree that there's no silver bullet here, right? There's no magic here. And for those of you who are machine learning practitioners, it's sort of what we call the no free lunch theorem, right? That everything, there's a compromise. You choose one method, it's good for one thing, but it's not good for everything, right? So then, for time series data analysis, what's the goal? What are we trying to achieve here, right? So let's maybe take a step back and leverage an illustrative example. So this is a time series, just 13 data points, n equals 13, so n is the length of your time series. If I asked you, do you see anything interesting about this? Do you see any patterns here? I will tell you that nothing repeats itself exactly, right? So we can plot it. We can take a look, right? Again, typical things that we do with time series, right? We might see some things there. But when I approach time series, or basically any problem, I try not to go in with a solution in mind. And I follow this person. Does anybody recognize who this is? Right. So you might recognize this person as Lord William of Ockham. And he's very popular. He's known for something called the law of parsimony, or more commonly referred to as Occam's razor, right? Which simply states that simpler solutions are more likely to be correct than complex ones. And this is what drives me as a reformed scientist, right? Is how do we approach things, and how do we approach time series analysis? So I asked myself this one question. What's the most simple and intuitive approach that I can take to analyze time series? So going back to our illustrative example, we have to make a definition first, because again, we're not interested in the full time series, but let's take a smaller section of this. And the definition is a subsequence. So a subsequence is a part or section of the full time series. So for example here, this is a subsequence. So it's not the full time series, just a chunk of it. This one can also be a subsequence, right? Or 7 data points could also be a subsequence. So that's what we want to take a look at. Now we have to then choose what is the subsequence length. So in this case, we're choosing, let's say, m equals 4. So m is a subsequence length. And I can then now say, well, how does this subsequence compare to somewhere else along that time series, right? Because we want to know, where should we start looking? Where should we start exploring? So in order to compare subsequences, we've got to take something called Euclidean distance. And the definition of the Euclidean distance is the straight line distance between 2 points, right? What does that mean? Well, I'm not that smart, right? So I'm going to make this simpler. Let's use just simply 2 points, right? M equals 2. And I can plot them. So that's one of my points, the green box. I can plot the other one. And the definition says that the distance, Euclidean distance between them is simply the straight line distance. And this is Euclidean distance. I don't have to give it a fancy name. I can just call it h for simplicity. Draw some lines, right? Add some variables. Now we know how to calculate that Euclidean distance, right? Take the square root of both sides, we get h. And we all recognize this, right? As masquerading as Pythagorean theorem. Very, very simple, right? High school, maybe even junior high school math, we know how to do this. And so we plug in our points in there, and we can very quickly calculate the distance between these two subsequences, right, is root 2. Now, what does this mean if we add an extra data point, right? So in this case, we're adding these. All we got to do is just simply add a C to this, right? Sorry. Let's get there. OK, add C to it, and then we get root 3. So as we move on, now we're at the stage of how do we do it for a subsequence of 4, right? Very, very similarly the same thing. But that's only comparing 2 subsequences. What if I want to do all pairwise comparisons here? So what I then have to do is think about, well, let me repeat my sequence, right? And I want to store the distances that I'm calculating in another vector, just so you can visualize this, right? I'm going to compare these 2 subsequences. They're identical, so the distance is 0. I slide the second one over by 1, calculate the distance again. And I keep doing this all the way across, right? Done. So these are just pairwise Euclidean distances. But then I can ask a question. What is the other subsequence that best matches that green one? Now, there's what we call the trivial match, which is you're just matching yourself. That's not interesting, because that's obvious. But what we can do is look at the next best match, which is just over here, the 6.9. And we're just going to blank out that trivial match. And we can repeat this process by now taking our original subsequence, slide it over, right? And perform that same calculation over again. In this case, we find that the best or second best match is all the way at the end there. And we can do this for the entire thing. We can just slide this green box all the way over, the sliding window, and then calculate all of the pairwise matches. And this vector of distances at the bottom is just called a distance profile. A very simple name, right? But if we stack all of these distance profiles on top of each other, it's called a distance matrix, or pairwise Euclidean distance. And again, I've highlighted all of the places, right, where there was the smallest match. So great. We have a simple, intuitive approach that we've taken. But there's a question of, is this solution scalable? Well, let's take a look at this. It turns out that if you were to plug this into your favorite computer algorithm, right, in my case, it's Python, it's only a handful of lines of code. But to understand the computational complexity, we just have to examine these three for loops. That's really all it is, right? And that gives me O of n squared by m. Again, n is the length of your time series, m is the subsequence length. And the space complexity is also n squared. Nasty, actually, right? And if we were to actually do a brute force calculation of a slightly longer time series beyond 13 elements, right? This is what it looks like. Literally a back of the envelope calculation for you here. So if I was collecting data 20 times a minute, so that's basically every 3 seconds, I collect a data point for 60 minutes per hour, 24 hours a day, 365 days a year, right, for 5 years, right? Collecting data every 3 seconds for 5 years. There might be some sensor data or whatnot, right? This amounts to a time series that is just over 52.5 million data points that you've collected. And if I were to use that brute force method to calculate that pairwise Euclidean distance, it would take me roughly 4.4 years. And not only that, but about 11.1 petabytes of memory would be required to store. Or you can write it to disk if you want it, if you're crazy, right? Right? It's an unenviable task. So is the solution, the brute force solution, scalable? Not really, okay? And that really explains why, at the beginning, people are using all of these methods. Because either they're more interpretable, perhaps, but mostly it's because it's more scalable, right, for large amounts of data, especially when it comes to deep learning. Until now. And so recently, in 2016, there were a group of researchers over at UC Riverside, University of California, Riverside, as well as the University of New Mexico, that published a series of back-to-back papers. And I only stumbled upon it on, believe it or not, a subreddit, okay? And I should point out that all of the work that you're seeing here today, the underlying research, was not done by me. It was done by these researchers, and they're not necessarily collaborators of mine. I have reached out to them, exchanged emails with them about, for further clarification. But all the credit really goes to them. It's a beautiful amount of work that they've done. And they've, since 2016, published about 13 papers built upon this fundamental idea of something called a matrix profile. A matrix profile. So what is a matrix profile? A matrix profile is simply a vector that stores the distance between each subsequence within a time series and its nearest neighbor. What does that mean? So going back to our picture, All this means is that we don't store the entire n by n array. All we're interested in are just those numbers, right? And that's the vector that it's talking about, just the minimum distance to its nearest neighbor. That's all we care about. And if we only store that, the space complexity is O of n, right? Very manageable. Now, if we take, so why is this useful? So if we take our original illustrative example, right, and we take our matrix profile, we can actually plot these or annotate our original time series right underneath it, and this is what we get. So this is our matrix profile, and if we're asking the question, what's the best match? All we need to look for here is the minima, right? So this sequence right here of 1, 3, 2, 9, right, has the best match with something over here, right, which is 1, 2, 2, 10. And similarly, with his matrix profile, you can look at outliers too. What doesn't have a good match and therefore has a large distance? But there's a whole bunch of other things that you can extract out of this matrix profile. A lot of times you can get things for free. So now, again, this is the research that was done. So the researchers looked at comparing it to brute force analysis, which we just computed. But the first algorithm that came out with was called STAMP. And it is taking all of that math and applying a very nice fast Fourier transform to it. And they went from a time complexity of n squared by m to n squared log n. Significantly better. Then the next paper that they published called STOMP, they threw away the fast Fourier transform and just looked at the math. And from the math itself, they were able to get it down to n squared. And this is an exact solution. This is no approximations. Oftentimes, when you have these types of Euclidean distance calculations, they apply some approximations or some heuristics. This is an exact solution. You will not get any false positives. And then finally, they ported this over to GPUs, right? Just throwing hardware at it to make the computation even faster. So what they did was, so I was looking at about 52.5 million data points. They went crazy and went for 100 million data points, right? They took n equals 100 million, used their GPU stomp calculation, and what they published was that it took 12.13 days, right? Instead of, I think it says down there, just over 1,500 years if you did it in brute force way. Okay, think about that for a second. And so this is one of the corresponding authors, Eamon Keogh. He says, given the matrix profile, most time series data mining problems are trivial or easy to solve in a few lines of code, of extra code, after you've computed the matrix profile. And he also goes on to say, these are the best ideas in the time series data mining in the last 2 decades. And to me, anybody who says that must be a gangster, okay? But of course, bringing it back down to earth, there's another scientific gangster that I like that says that, or popularized the phrase, extraordinary claims require extraordinary evidence, right? And that's the late Carl Sagan. And so that's where I embarked with TD Ameritrade on validating whether or not this was for real. So I built an initial prototype. I'm a Python guy, using NumPy for some of the numerical computing, right? And I compared, not for 100 million data points, just simply for just 2 million data points, 2 to the 21. Their GPU implementation said that it takes about 9 minutes. I did it on a single CPU, too long. It doesn't even register on this bar. But then I asked, well, it does work. It does compute for smaller data sets. And it makes me a sad panda. So I thought, well, what if I parallelize, right? I have multiple threads, multiple cores, and I'm using another fantastic open source piece of software called Numba, which takes your Python and NumPy code and JIT compiles it. So you nearly get C-level performance out of the box. And within 2 days of taking my original code, I was able to parallelize my algorithms, right, across 16 CPUs and brought it down to about 3 hours. Still not great, but progress. And then that's when I realized that there's a space here that's missing, right? We went from single CPU stomp to GPU stomp. What's missing here is maybe some sort of multi-core distributed computation. And that's where I leveraged, the last speaker talked about Dask. So I leveraged Dask out of the box to distribute my code and my computation. And I was able to take it from 16 CPUs to 128 CPUs in 5 days, right? So think about this. Traditionally, if you have to write distributed code, it becomes very, very painful. I did this in 5 days, okay? And I'm not that good. I'm not a software engineer, right? And that brought that down to about 13 minutes, right, for 128 CPUs. So not bad, but being very competitive, I asked, well, what if we just went to 256 CPUs, right? And this was on the full 100 million data points. We were actually able to get it done in just under 10 days, beating the GPU stomp implementation. Now, let me be very clear, because I've been harassed about this, right? I'm not at all saying that CPUs are faster than GPUs. I would be an idiot to say that, right? But the point here is that with open source tools such as things like Numba and Dask, we are able to do things very quickly, right? If it wasn't for these open source tools, I wouldn't have been able to talk about this. So going back to the original question, is the solution scalable? I think Amon was correct, that there is something here. And so our distributed implementation, sort of playing along based upon a play of words of stamp, stomp, we call our implementation stump, because we're in Tree Town, Tree City, Ann Arbor. But our distributed version is called stumped, okay? So, but more importantly, what I'm excited to announce today is that recently we open sourced all of this software. And the open source library is called Stumpy, or Stumpy, if you will. So what is Stumpy? So Stumpy is a powerful and scalable Python library that efficiently computes the matrix profile, which can be then used for a variety of time series data mining tasks, right? So these are some of the things that you can do. You can do motif discovery, which is finding patterns within your time series data, anomaly detection, right? Just for free, essentially. Something very interesting called time series chains, which is if you have a repeatable pattern that sort of trends toward a certain direction, there's a way that for you to identify that just by looking at your matrix profile that comes out of the box with Stumpy. Also think about multiple dimensions, so having multiple time series, right, that may be collected from different sensors. You can leverage Stumpy for this as well. And then further, you can segment your data if you're trying to find different change points within your data. There's thinking about clustering, so the original authors have described something called MPDIS, a distance metric. Snippets, given many time series, many subsequence or patterns that you have that look similar, how do you choose one representative one to show, right? So that's what snippets, and there's many more things. I'm only scratching the surface. I recommend you go and Google UCR, University of California, Riverside, and matrix profile, and you'll find a ton of information. And so Stumpy is open source. You can follow us at stumpy_dev, but it has fully unit tested, 100% code coverage, whatever that means. Minimal dependencies, but only supporting modern Python, not legacy Python. If you have your Python installed, 3.5 or more, you can just do a pip install Stumpy, and that should install. Otherwise, find me in the hallways. Or if you're cruel to yourself, you can download the source code and install from there. With that, I would like to conclude. I will be outside for coffee, and I'll be also here for the reception. So please come and chat. Use the code, contribute, file issues. Any feedback would be great. Thank you for your time.